Hello everyone. In this video, we're going to start with a motivating example for section 8. Section 8, which is on primitive roots and the multiplicative order of congruence class modulo M. And the motivating example is coming from repeating decimals. So actually we know, or it's actually proved later in the book, that a fraction is a repeating decimal. The decimal expansion in base 10 of a rational number will be a repeating decimal. So the question is, how do we know how long that repeating part, the period of the decimal, how long is that going to be? So let me show you some examples of this. So I'm going to look at three numbers, 3 over 11, 5 over 37, and also 1 over 17. And they seem about the same level of sophistication, these three fractions. So let's see what their decimal expansions are. It turns out that 3 over 11 is 0.27, 27, 27, etc. So we see that the repeating part is 27, so this is actually 0.27. The period is of length 2, and is just 27 repeating. What about 5 over 37? 5 over 37 is 0.135, 135, 135, etc. So the repeating part is 135, and the length of the period is 3. Okay, how about 1 over 17? It turns out it is 0.058823529411764 and then 0588, etc. So the repeating part is actually really long. 058823529411767. And the question is that why is it that this is of length 2, this is of length 3, but this is so long? How do we figure that out? And can we know that a priori what the length of a period is and what is the reason for those very long periods? Okay, so let's try to figure that out. How can we figure this out? Well, let's start with an example. Let's start with the fraction 3 over 11. And to figure out what the decimal expansion is, we do a long division. So we would do long division of 3 by 11. And well, 3 is less than 11. So we start with 0 point. And this will be 2 times 11 is 22. Minus 30 minus 22 is 8. And then 8 is less than 11. So bring another 0 here. And now 0 here. So this is going to be 11 times 7. That's 77. And 80 minus 77 is 3. And now we see that, okay, when I bring one more 0 here, now I'm just like going to do the same calculation that I did before. This is times 2. This is 22, and subtract, and I get 8. And then there's going to be a 7 and a 2 and a 7 and etc. Okay, because I'm just going to be repeating from here on. I'm going to be repeating this calculation over and over again. Okay, so what is it that happened? I'm going to do now the same calculation by using long divisions, which is what was happening along the way. So we started with 3 and tried to divide it by 11, and we saw, well, that's impossible. And or the quotient is 0 and the remainder is 3. And then what we did is take 3, multiply it by 10, make that 30, and now divide by 11. So now dividing by 11, 30 by 11 is 11 times 2 plus 8. Then took this 8, multiplied it by 10, made it an 80, and divide by 11 times 7. That is 77, which is a 3. And then keep going like this forever. This is 30, which is 11 times 2 plus 8, and so on. Okay, and it just keeps repeating because now as soon as I saw a repetition here, you see, as soon as this number repeated from 1 above, the calculation is just going to repeat. So this part here is just this part here over and over again. Okay, great. So we see why it's going to keep repeating and why we're going to be getting the 27 and 27 and 27 repeated. So another thing to notice is that this column here is actually the decimal expansion is there. But the reason for the repetition came from the fact that this number repeated itself. Okay, so what's that number? That number is a remainder of division modulo 11. And when that number repeats, we get a repetition, and then we see that the process is going to just like cycle. So how can we figure out when that's being repeated? So what happens is that we started with, well, with 3 times 10. And if I just look at congruence, I am only caring about this number here. I can use congruences modulo 11 and figure out what that number is. So what this equation says, the first equation here, is that 3 times 10 is modulo 11, it's 8. Modulo 11, and then I took that 8, multiplied it by 10, and figure out that that is 3 modulo 11. But notice that 8 was 3 times 10. So this is 3 times 10 times 10. So what this is actually is 3 times 10 squared. That was 3 modulo 11. And the fact that I got a repetition right there, that the 3 appeared again, that's when I can stop. And that's going to give me the repetition that I wanted, and is going to make the cycle start. So right there, this number, the fact that it's 2, the length of the period is 2 because of that 2 over there. Let's see what happens. So by the way, this equation right here, because 3 is a unit modulo 11, 3 and 11 are relatively prime. This also implies that 10 squared is congruent to 1 modulo 11. And if you see what happens in the repetitions, what is actually happening is that every time I'm taking this number and multiply it by 10, so this would be 3 times 10, this would be 3 times 10 squared, and I would do 3 times 10 cubed, 3 times 10 to the n. And whenever 3 times 10 to the n gives me back 3, that n is the length of the period. Let's try it again with what was the other one we had here, 5 over 37. Let's see that for 5 over 37. So with 5 over 37, what was happening is that we would start the calculation with 5 over 37 times 0, that's 5. And then multiply by 10, that's 50. And 50 is 37 times 1 plus 13. And then take 13 times 10, that's 130, and divide by 37, that is 37 times 3 plus 19. Okay, no repetition yet. And then take 19 times 10, and that is 190, and that is 37 times 5 plus 5. And now we see the repetition here. So the length of the period will be 3, is this 135 that we already see here. Okay, and we see the period is going to be 135, and it is there. But if we only care about the length of the period, what I can do is just use congruences. So I start with 5 times 10, that is 50, and modulo 37, that is 13 modulo 37. And then multiply by 10. So 13 times 10. But again, 13 times 10 is 5 times 10 times 10. So this is 5 times 10 squared. that is 130, and modulo 37, what I'm saying is that this is 19 modulo 37. And then compute 5 times 10 cubed. That is 5 times 10 squared times 10. 5 times 10 squared is 19 times 10. That is 190. And 190 is 5 modulo 37. And now we see that there is a repetition, that 5 times 10 cubed is congruent to 5 modulo 37. And the repetition is going to start because what is the next one? The next line would be 5 times 10 to the 4. And 5 times 10 to the 4 is 5 times 10 cubed times 10. But 5 times 10 cubed is something that we've calculated. That is 5 times 10. And that is 13. Modulo 37. So now we see that the repetition has started because now it's that 13, 19, 5, 13, 19, 5, 13, 19, 5. So this actually is what implies that there will be a repetition, and the repetition tells me that the length of the period is 3. So what happens with 1/17? Why was the length of the period so long? By the way, this happens because you see that 5 times 10 cubed, or really 5 times 10 to the n, will be congruent to 5 modulo 37. Since 5 is a unit, this will happen whenever 10 to the n is 1 modulo 37. So 5 to the 10 to the n will be 5 modulo 37. The repetition will happen for the first value of n, such that 10 to the n is congruent to 1 modulo 37. So the very first time that a power of 10 becomes 1 modulo 37, that n will actually be the length of the period. So we can try to figure out then what is the length of the period for 1/17, or the length of the period in the decimal expansion. The length of the period, so if the length is n, n is the smallest positive integer such that 10 to the n is congruent to 1 modulo 17. Because what we're going to do, the way we're going to compute the length of the period, the way we would compute the decimal expansion itself would be 1 is 17 times 0 plus 1, and then 10 is 17 times 0 plus 10, and then 100 is well, 17 times whatever it is here plus whatever remainder, and then take that remainder, and that's going to be 10 times the remainder, but that remainder is already, in terms of congruences, this says that 1 is congruent to 1 modulo 17, and then 10 is congruent to 10 modulo 17, and then now I want this 10 to repeat itself. And then we're going to see that, well, then like 10 squared, that's going to be what? Modulo 17. So that's what I want to figure out. When am I going to see a power of 10 to be 1 again? Okay, so when is it going to be that 10 to the n? Whenever I get a 1 here, then the cycle is going to start again. and that's going to be the length of the period. Okay, so maybe we can try to figure out what the first time that happens. I can make a little table here of powers of x modulo 17, and then powers of x. So, and then the one we want is 10 in particular. So 10 square 100 turns out to be 15, then it's 14, then it's 4, and et cetera, et cetera. It turns out that the first time this happens, the 5 is 6, 9, then 7, x to the 8, x to the 9, x to the 10, x to the 11. I have here that is 5, 16, 7, 2 to the 11 is 3, then x to the 12, x to the 13, x to the 14, x to the 15, x to the 16. X to the 12 is then 13, 11, 8, 12 in 1. So the first time that actually this happens is 10 to the 16 is congruent to 1 modulo 17, and that is the first time this happens. So the length is 16. And if we go back to the actual fraction, we see that the length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the length is actually 16, which is what is predicted by this property of the congruences, which is the first power of 10, that is 1 modulo 17. So that is precisely what we're going to call the order of a number. Let m bigger than 1 and a another integer that is relatively prime to m, then by Euler's theorem, there is a power of a that gives me 1, and the very first time that happens, that is the order. We say, we define the multiplicative order of a modulo m to be the smallest positive integer n such that a to the n is congruent to 1 modulo m. And we will write order of modulo m of a to be n for that number. So what we just saw is that, for example, the multiplicative order of, so we saw, for example, here, for 11, we saw that the order of 10 modulo 11 is 2, 100 is 99 plus 1, so the order of 11, so the order modulo 11 of 10 is 2, the order modulo 37 of 10 was 3, but the order modulo 17 of 10 is 16. And that's why the length of the fraction, so in here, this implied that the period of 3 over 11 was of length 2. The period of 5 over 37 is 3, but the period of 1 over 17 is 16. So that those orders of 10 modulo those different numbers determines what is the length of the period in a decimal expansion. The decimal expansions will be brought back in section 8.9.2 in a lot more detail. But what we're going to do for now is talk about this definition and figure out how to compute that number and what properties it satisfies. That's what we're going to start doing in section 8.1. Correct. So we'll continue there.